Okay, so I guess our last keynote in the session, and this is Amin Vahdat returns. So if you have been following ONS, Amin has been part of almost every ONS as far as I can remember, and he has given multiple keynote talks, and he is back. So you may wonder why, and so one of the reasons is that if you look at the history, he is the the most hits on the box office in terms of the ONS archive website. His talks are always among the top 3, and the reason being that he always has brought some big development that Google has been part of, and shares something really interesting and exciting, both technical as well as what the implications are and what is possible in the world of SDN and NFV. So with that, I think I'll ask Amin to come and join us and share his thoughts as well.
Thank you very much, Guru. It's a great pleasure to be here. Always excited to come to ONS. Today's a particularly exciting day for us at Google, and in particular, Google networking. We're going to be telling you about some of our work in data center networking for the first time. We've been here in the past talking about wide area networking, of course, about network virtualization. Great. I want to start with acknowledgements. Literally hundreds of people have contributed to this effort over a decade. I thought about trying to list them, but I was worried about leaving some very deserving people off the list. Suffice it to say that if you were to rank order the set of contributors to what I'm going to describe today, my name would be very far down the list. So I am very grateful to have the opportunity to once again act as a mouthpiece for the work of a truly spectacular set of folks. We are particularly excited about networking because I think that networking is going to be playing a critical role for what computing means moving forward. So what you can see here is that distributed computing has really faced the same set of challenges since sockets were introduced in BSD 30 years ago or so now. And I think that's just about to change. So with the end of Moore's Law, either here or soon to be here in the next few years, how we think about computing necessarily has to change. And what distributed computing means is going to have to change. A key part of computing and how many people like to build their services is around storage. We've seen just tremendous increase in storage capacity, right? The sheer volume of data that you can process over has grown following roughly Moore's Law. But the I/O gap remains. What this means is that the distance between processors and the underlying data that they need to operate over is continuing to increase, right? So lots and lots of disk capacity. We've now gotten to the point where we can think of the disks spread across entire buildings as being available to any server. This is fantastic. At the same time, they're looking further and further away given the processing power that we have. Next generation flash is starting to make a splash, but still at scale in a distributed computing environment, it remains largely untapped. So we think that networking is at this inflection point, and what computing means is going to be largely determined by our ability to build great networks over the coming years. And in this world, data center networking in particular is a key differentiator. Okay, so what does this mean for Google technical infrastructure? We build building scale, warehouse scale computers, right? Just row after row of compute, row after row of storage. And over the years, we've put together some infrastructure to harness this compute and storage. Right? The list goes back more than a decade, perhaps starting with GFS, the Google File System, which showed how to, at the scale of tens of thousands of servers and disks, hundreds of thousands of disks, build essentially one file system. To MapReduce, which showed how we can basically do processing, query processing over this data. Bigtable, which led the NoSQL revolution, on and on and on. So if you look at this list, I think it would be fair to say that many of these efforts have defined what it means to do distributed computing today. But one of the observations that we've long had is that you can't build world-class distributed computing infrastructure without world-class networking infrastructure. Right? So how is it that we're going to connect all these servers together? Would you imagine building a system like GFS where you can harness the storage capacity of, say, 100,000 disks without having a world-class network to put it all together? So I think over the last few years, some of the pieces are starting to come into place with respect to some of the work that we've been doing in networking at Google. Right? So things like Google Global Cache, how we deliver content, including videos and static content from points across the world, to some of our work on B4, on wide area networking, et cetera, to perhaps some of our most recent announcements on gRPC going open source. So we are now making available the same remote procedure call infrastructure that we use internally at Google, available to everyone. So you get some of the same load balancing, flow control, multiple streams, all operating over HTTP2. That we use internally is now available externally. And we think that this can be a nice basis for building distributed services moving forward, again, not just for us, but for the community at large. A few years ago, we described B4, our software-defined wide area network that connects all our data centers across the planet together. This is a network that is actually bigger than our public-facing network. So the network that connects our data centers together is bigger and actually growing faster than our public network. So again, the computing needs and the data processing needs of our infrastructure is just growing at a tremendous rate. And we've shown how we've leveraged software-defined networking to build a cost-effective and increasingly highly reliable network. Last year, we were here telling you about how we leveraged the tenets of software-defined networking to build our network virtualization stack. Mark gave a very nice presentation on end-host SDN, and we approach things similarly with Andromeda. Basically, how do we take our underlying network infrastructure and slice it up for individual virtual machines, virtual clusters, if you will, with the illusion that they have their own high-performance network available to them? How do we open up the same kinds of network function virtualization that we've been taking advantage for building our services, like load balancing, denial of service protection, access control lists, virtual private networks, routing, et cetera, and make it available to these isolated networks running on top of our raw hardware? Today, in particular, I'm very excited to tell you about some of the work that we've been doing in the data center networks, the hardware and software that power these things. So for the first time, we're going to be showing you 5 generations of data center networks that we've been building at Google. We've been developing and deploying our own hardware, our own software to run our data center networks for the past decade or so. Given that distributed computing is in our DNA, it's perhaps not surprising that the software that we run on our network infrastructure looks a lot more like the distributed systems that we've built, say GFS, MapReduce, and Bigtable, than it does like traditional internet protocols. So one thing that you might see is that we've actually been practicing software-defined networking in our data center since before the term was really in existence. And I can tell you that in our latest generation data center networks, Jupyter, we run, of course, SDN and OpenFlow. Okay, so putting all this together, what we've been able to leverage is basically vertical integration across the network. So going from B4, our wide area network, to the Google Global Cache, which has our edge presence, to Jupyter, our building scale data center network, to Freedom, which is our campus level interconnect. Freedom is particularly interesting to us because we were able to leverage some of the same hardware and software that we deployed into our data centers to connect our data center buildings together within a campus. And that formed the sort of predecessor and example for B4. And finally, Andromeda, which allows us to virtualize all this hardware infrastructure, both across the local area and across the wide area, with the illusion that you have your own dedicated networking infrastructure running on, say, Google Cloud Platform. Okay, so with that background, let's take a look into Google's data center networks. What's different about data center networking? I think that actually data center networking affords huge opportunity. It's different in many, many ways, some of them challenging, some of them opportunities, different from traditional internet networks. I think the biggest opportunity here is that it is run by a single organization, and it is pre-planned. So relative to the internet, capital I internet at large, where you have to discover what the network looks like, you actually know what the network looks like in the data center. You planned it. You built it. Right? And given that, you can configure it in a central way rather than having to discover it as you go along. Overall, the point about the data center is that because it's under the control of a single organization, the software that you can run can be very different, and it can be optimized to the key characteristics of the internet rather than necessarily having to interoperate with 10 years, 20 years of legacy. So what we found a decade or so ago is that traditional network architectures, hardware and software, just could not keep up with the bandwidth demands and the scale of our distributed computing infrastructure in the data center. So essentially, we could not buy for any price a data center network that would meet the requirements of our distributed systems. We faced substantial operational complexity from box-centric deployments. And what I meant by that is that even if we were to buy the biggest data center network that we could from our favorite vendor, the model for operating these networks was around individual boxes with individual command line interfaces. And we'd spent some amount of time already figuring out how to manage thousands, tens of thousands of servers as if they were a single computer, tens of thousands, hundreds of thousands of disks as if they were a single storage system. So the notion of having to manage, say, 1,000 switches as if they were 1,000 switches didn't make a lot of sense to us, and it seemed unnecessarily hard. So both from a can we buy it and can we run it perspective, we set out to build our own network because we found that the existing infrastructure just didn't meet our needs. So we were inspired by what we learned in the server and storage world. We were inspired by scale out, right? Rather than figure out how to buy the next biggest network and the next biggest router, we wanted to be able to scale out our switching infrastructure, our routing infrastructure, with additional commodity elements, just as we did with our servers and storage. Why couldn't we plug in another network element to give us more ports and more bandwidth as we needed it? Along these lines, we basically, in retrospect, pulled out 3 key principles that work together to allow us to build our data center networks. First, we leveraged cloud topologies. This is an old idea, 60 plus years ago now, from the telecommunications industry. The notion here is that you can leverage a number of small commodity switches to build an effectively non-blocking, very large-scale switch. And it can scale more or less infinitely, and certainly to the size of the data centers that we needed. We did this with merchant silicon. So in the data center, we did not have all of the requirements of the wide area internet. In particular, we didn't necessarily need massive routing tables, and we didn't need deep buffering. As such, we could leverage commodity merchant silicon to build our CLO-based topologies in the data center. And finally, because we planned and deployed our data center networks, we could leverage centralized control. And what I mean by that is that we would have software agents that knew what the network should look like, that could affect routing along those lines, and that could react to exceptions as exceptions to the underlying plan. Right? Just from an algorithmic simplicity perspective and algorithmic complexity perspective, imagine that if you know what the network should look like, you can have a much easier job keeping the network running that way than if you're constantly trying to discover what the network might look like and how the network is changing. Right? If I'm going to change the network, I'm going to tell my centralized control infrastructure, I'm going to change the network. So what I'm saying about what's different about the data center is it can be a simpler problem. Right? What drew me and many people to networking and networking protocols originally was the beauty of the problem. But beauty can sometimes mean how hard it is. So can we define the problem to be simpler and actually make it more scalable, make it easier? What we found is that our approaches to data center networking also applied to the campus network, how we could connect our buildings together, and to the wide area network. So to some extent, we've talked about our work in networking in reverse order. So we told you about what we did in B4, what we did in Andromeda for the wide area network and for network virtualization. But actually, both of those systems were inspired by and informed by our work in data center networking, where we'd been practicing building our own hardware and our centralized control infrastructure for many years. This chart just illustrates the growth that we're seeing. Shows you over about a 6-year period that our data center network bandwidth growth has gone up by a factor of 50. So again, the amount of bandwidth that we have to deliver to our servers is outpacing even Moore's law. And what this means is that we have to be able to scale out. We can't continuously rip out and put in new networking to keep up with these bandwidth needs. And very briefly, the scale that we operate under drives our architecture. These are not necessarily reflective of any of our networks, but you can imagine that typical networks today might have 10,000 plus switches, 250,000 links. They might have 10 million routing rules. How you deal with networks of this scale is fundamentally different than what you might at somewhat smaller scales. Okay, so why is it that we needed to build networks at the scale of entire warehouses? So one thing that you could say is, were we trying to solve a problem that was too hard from the perspective of the size that we were trying to get to? Right? So these buildings, you saw row after row after row of compute. Some of the largest data centers out there have tens and tens of megawatts of compute infrastructure. Why do we need to get so big? One answer is that there's substantial resource stranding if we cannot schedule at scale. So I won't go into the details here, but imagine that you have shared infrastructure, as we do at Google, and that you have a number of different jobs that you'd like to schedule on that infrastructure. If you have to schedule jobs within the boundary of a single cluster, and you have, say, 10 1,000 server clusters versus one 10,000 server cluster, you will get much, much better efficiency if you can schedule arbitrarily at that larger granularity. Right? So if I can place my jobs anywhere across 10,000 servers, rather than have to fit within 1,000, the numbers actually work out to be quite stark. So if we could build a network that could scale to an entire building, we get much more efficiency out of our compute and out of our disks. And those actually wind up being the dominant costs. The network can be quite inexpensive and can be quite an enabler for compute and storage. Once you get to that scale of the building, you have to make sure that you deliver sufficient bandwidth. Right? So that's where what I call balance matters. An unbalanced data center means that some resource is scarce and it limits your value. And if that resource is scarce, that means that other resources are sitting idle, which is going to increase your cost. Typically, certainly at data center scale, the resource that is most scarce is the network. Right? We tend to under-provision the network because we don't know how to build big networks that deliver lots of bandwidth. As one rule of thumb, Amdahl put together 1 megabit per second of I/O for every megahertz of computation for parallel computing. Let's see how that plays out in the data center. So imagine, again, these are sort of fictitious, but perhaps based on reality numbers that you might see in a data center in the near future. Compute servers might have 64 2.5 gigahertz cores. And since I'm not a computer architect, I can cheat and follow Amdahl's law and say that I would need, well, maybe 150 gigahertz of bandwidth. Let's round down a little bit and say that each of those servers, to be balanced, needs 100 gigabits per second of access to I/O. Remember, going back to Amdahl's law, I/O today is all over the network, right? The local I/O doesn't matter. You want to access data center-wide I/O. Of course, you have disks, but increasingly you're going to have flash that's capable of 100,000 IOPS with 100 microsecond latency. And in the years ahead, we're going to increasingly benefit from non-volatile memory that promises maybe 1 million plus IOPS with 10 microsecond or less access latency. It's not unreasonable to imagine that this data center has 50,000 servers. So if we follow Amdahl's rule of thumb and just multiply through 50,000 servers by 100 gigabits per second per server, you would need a 5 petabit per second network. We'd want to build a 5 petabit per second switch. And even if you think I'm unreasonable in my goals for the scalability, maybe you're going to oversubscribe the network by 10 to 1. That's a fairly large oversubscription ratio. You'd still need a 500 terabit per second data center network to come close to achieving balance. Put that in perspective, 500 terabits per second is more capacity than the entire internet today. Right? So if you were to measure how much bandwidth goes back and forth across the capital I internet, it's, of course, hard to pin down, but probably in the 200 terabit per second range. Okay, and of course, I need to have this to achieve my goals of disaggregation of my storage infrastructure. I need to have predictable low latency. Right? It's very easy today to disaggregate disk that best case has 10 millisecond access latency. I can make that look local across my network. My network's faster than that. But Flash and NVM are going to make that much harder. Now, put that together, I have a building worth of computes, and I need to introduce new servers continuously. I need to upgrade these servers to go from 1 gigabit per second to 10 gigabits per second to 40 to 100, and then to who knows what. I can't take down my building to do so. Right? The investment is just too large. I have to be constantly refreshing my infrastructure, upgrading the network, having the old live with the new, without interrupting very much capacity at all. Right? So that means that scale-up networking doesn't work. I can't do scorched earth upgrade of a network that crisscrosses the entire data center. So this says that we need a data center network infrastructure to support Google scale, performance, right? So building size, performance meaning balance, and availability, right? We work very hard to deliver the highest levels of availability, and the network is key to that. If you have your network fail, very, very high probability that someone's going to notice, right? So we have to fail last, and we have to fail least. All of this then forms the underpinnings of Google Cloud Platform. One of the things that we're particularly excited about is that we're now opening up our compute infrastructure such that engineers across the world can take advantage of what we've built. What we're really hoping for is that the next great service can leverage this infrastructure and the networking that goes along with it without having to invent it. Okay, let's come back to software-defined networking and what this all means. The simplest definition that we've seen bandied about is we're going to split the control plane from the data plane. We're going to run the software on high-powered servers. I think it goes a little bit beyond that. It's not about hardware-defined networking versus software-defined networking. It's about a software control plane that abstracts and manages complexity. It's about moving beyond the box. It's about changing the interface to your network to not be about standard protocols, but being about the software control plane that manages the complexity, hides it, that takes 1,000, 10,000 switches and makes them look like one. The hardware, of course, is going to be there. Accelerators are going to be there. But how do I manage it as if it were one large entity? That's what it comes down to on the server side, on the storage side, and of course on the network moving forward. So in the interest of time, I'm not going to have a chance to go through much of the details. I'll just show that we started in the same place that everyone else did in building our data center networks with what was called a 4-post cluster network. And the size of our networks and its bandwidth was determined by the biggest, largest router that we could buy. And when we needed more capacity, we had to go build another data center network with the next biggest, largest router that we could buy. The approach that we've taken around cloud topologies is to take commodity switch silicon and build across 5 generations networks that look very much like this, with subtle changes here and there. We have top-of-rack switches that connect our servers together, and interestingly, the same switch silicon that powers our top-of-rack switch then powers our aggregation blocks that provide connectivity among some number of racks. And finally, the same silicon that powers our spine layer that connects the edge aggregation layers together. Right? So this hierarchical cloud-based topology says leverage merchant silicon in a cloud topology to provide high bandwidth at the scale of a building. Okay, so I will skip the details. Essentially, we've increased the aggregate bandwidth that we had available to us approximately 10 years ago in our 4-post clusters from 2 terabits, you see that in the upper right, to our latest generation Jupyter fabrics that achieve over a petabit per second of bandwidth at their maximum scale. So we started with Firehose 1.0. Firehose 1.0 didn't actually see production, but it's considered a seminal effort within Google. We tried to integrate networking with servers for a variety of reasons. It didn't work out. So we actually used very much the same technology and built more traditional looking switches, and Firehose 1.1 actually went live. Interestingly, we actually had to build our 4-post clusters at the same time as our networks because we weren't quite yet sure if we could deliver the requisite levels of availability. So we deployed our networks as a bag on the side, meaning that all our servers connected to both our pre-existing cluster routers and our next generation close. Once we got to a high level of confidence about our infrastructure, we actually then, of course, eliminated the 4-post routers. Watchtower was the first in-house network that went across our infrastructure. So it powered all of Google for some period of time. And you see 4 of these chassis, 128 ports of 10 gig each, powering one of the edge aggregation blocks that I told you about. Next, we deployed 10 gigabit per second networking with the next generation of merchant switch silicon at the top of rack with a project called Pluto. This was our first 10 gig effort to the servers. And the same exact, again, switch chips went into our 4th generation Saturn networking infrastructure. What you see here is 288 ports of 10 gigabits per second, once again making up an edge aggregation block. And finally to Jupiter, our current generation networks, leveraging the latest generation of merchant silicon. So this is a picture of a Jupiter super block. You might be thinking that you've seen better looking switches, but let me assure you that beauty is in the eye of the beholder. This switch delivers 80 terabits per second of bandwidth. I won't make you count all the ports with a magnifying glass. It hosts our SDN software stack through OpenFlow, remotely controlled via some servers, and again powers all of our data centers at this point with the balance that we require. So very, very briefly, since I'm now over time, what about our software? So you saw our multiple generations of hardware. In the early days, we faced a choice for our control plane. We could go with existing routing protocols that we were familiar with, like OSPF, ISIS, BGP, etc. Or we could build our own. We chose to build our own for a variety of reasons that I summarize here. The first and probably the most important was the limited support for multipath forwarding. The topologies at the time, I should mention, so remember that we're now talking about a decade ago. The topologies that we were considering needed multipath forwarding and very efficient use of multipath to work, right? Relative to some of the other topologies you saw in the existing work, we needed lots and lots of paths between each source and destination to be available to us to achieve the bandwidth that we did. And existing protocols just didn't have great support for that at the time. Remember that existing internet protocols are about connectivity, finding a path from a source to a destination, not necessarily the best path, and certainly not multiple paths. Okay. 10 plus years ago, there were no high quality open source stacks. So again, what we evaluated wasn't necessarily going to meet our needs. All of these protocols were based on broadcast, and at the scale that we were looking to operate, remember entire building scale, we were quite worried about the scalability of these broadcast-based protocols. And of course, once you install these broadcast-based protocols, you were likely left with needing to configure each of the network elements as an individual box. And I already mentioned some of the challenges that we faced in trying to run our network in that manner. So putting this together, the new conventional wisdom that we had been learning at Google from the early days in building massive systems at scale. Logically centralized. Now, logically centralized doesn't mean a single server that's controlling everything. But logically centralized with a hierarchical control plane with a peer-to-peer data plane beats full decentralization. And we've seen this play out over and over again. And we saw it play out in our data center network as well. Scale out is much more convenient than scale up. We saw this with GFS, with MapReduce, with Bigtable. We told you about it with B4 and Andromeda. And we actually practiced it from the early days in our network. Centralized configuration and management dramatically simplified all the system aspects of running this network as well as deploying it. Okay, I won't go through the details of our early control software. We will be publishing a paper with full details. So this shows how we ran things on our Firehose, our Watchtower, and our Saturn networks. We have a new generation of control software that we run on our Jupiter networks that we'll be describing hopefully in the near future. But essentially, we had a set of elected central controllers that knew what the network should look like, that would collect link state from all of the routers, switches spread across the network, and redistribute this link state to everybody such that they could calculate their forwarding tables. We had to do some special things on our embedded stack running Linux, especially to integrate with BGP at the border of our network. So we have a cluster network, but of course, the cluster network is not an island. At some point, we had to integrate with the rest of Google's network infrastructure, and that was through BGP. And finally, we had a single configuration for our entire network. And the single configuration could be pushed to all switches, with each switch knowing what role they had to play in this ensemble. Again, dramatically simplified how we managed our network and how we ran it. Okay, so let me wrap up to leave just a few minutes at least for questions. We do see computing at a crossroads. Distributed computing has faced similar challenges over the past 30 years. We think that's going to be changing as Moore's law slows down to ends. The I/O gap is huge. The opportunity is to access global data center storage as if it were local. This is going to get harder and harder with flash and NVM. So we do see networking as a key enabler and a key differentiator for enabling next generation compute infrastructure. SDN is going to play a key role. Opening this all up, of course, to the Google Cloud Platform is going to give, I think, many people opportunities to leverage these innovations. Thank you very much.
Wow. So I mean, pretty amazing. I mean, I think this is mind-boggling in terms of when you talk about the scale and what you have been able to accomplish. But I want to ask you a personal question. We haven't had this conversation in a while, but I want to ask you because this is an opportunity. Almost 7 years ago, you wanted to do a startup. And you had a data center architecture. And that architecture reminded me of what I saw today. So tell me your personal journey in terms of you started with those ideas, went inside Google, probably found out that, oh, Google is doing something similar. How has that been? I have not asked personal questions before, but I think I couldn't resist it given what I learned just today.
It's been incredibly fun and gratifying. I wish I could give a different answer, but what's happening at Google, what was happening and is happening has been spectacular. And for me personally, it's been gratifying.
Is it okay to post that 7-year-old presentation to go with your this presentation?
It's on the internet, so I don't think I could stop you.
Okay, good. Any questions for Amin? Are you guys stunned? That's why I don't want to ask. Or, I mean, 1.3 petabits per second in a data center. I mean, I can't even comprehend what that means. So, oh, you have a question. Okay.
Yes, thank you very much for a very interesting presentation. Could you comment on your views regarding potential for optical switching technologies in the future?
So I think that there is a lot of different opportunities around optical switching. Moving forward, the question is, can we get to optical packet switching? So the challenges that we have in the data center is that depending on how you do things, optics can dominate your costs for deploying the network. So moving forward, a key bottleneck is going to be how do you drive down the cost of those transceivers that are continuously doing optical to optical conversions. Right? This is a big, big challenge. How you do that is beyond my area of expertise. It seems to still be at the science fiction stage, but we're very much looking forward to realizing some of those challenges.
Hey, Sanjay from Purdue University. A really nice talk. So the question I have now is, as a university academic researcher, where is the area we can have maximum impact? So obviously there are certain directions that we probably shouldn't be pursuing given all the work that you guys are doing at Google and Microsoft. So where do you think, what would you advise university researchers?
I think there's a huge amount to be done here. So some of the big problems are around network management, I would say, today, and network configuration. This is something that we work hard at. We've benefited from having a deep partnership with our network operations team that's allowed us to deploy some of these innovations. But essentially how you, again, run your network for the highest levels of availability while maintaining innovation velocity is a key challenge. Right? And then there's lots of deep aspects to that in an SDN environment. So the sort of generic question I'll ask is, what does management mean in an SDN environment?
Thanks.
Hi there. I wonder if you could please comment on scaling of table sizes when you build fabrics of this dimension.
You know, it's always, you always want more, I think, in terms of table sizes, but I would say that it doesn't typically hit my top 10 in terms of being able to build the data center networks that we want to build. What I mean by that is that we wish that we had larger table sizes, but it winds up being something that our very clever engineers can typically work around. We're not running the internet. We don't have millions of prefixes and growing that we have to deal with. So again, because we design the network, we can figure out how IP addresses are assigned. We can change multiple things. It winds up being a largely solvable problem. Still, if you told me that you could give me 2x the table space for free, I'd be pretty happy.
Oh, go ahead, okay.
Hi, Amin. You've talked about SDN in the WAN, SDN in the data center. With Google Fiber, are we going to see SDN being pushed out to the home?
That's a good question. I'm not sure. I could put lots of interpretations on that question. Maybe the easiest answer is going to be that likely it's inevitable if you look at the complexity of the home network today. So if you believe in the Internet of Things, and I do, moving forward, I don't think that many people could try to manage that complexity. I mean, probably the people in this room would not want to, even if they could. And so this means that if it's going to spread across the planet, we're going to have some different model for managing, configuring, et cetera, all these devices. So inevitable would be the easy answer.
Thanks.
Can I insert one of my own question before you get to ask a question? So, I mean, you said you're opening up this data center for other people to use. And so this may be one of the first time that other people have access to a capacity of this type. Can you give example of somebody really making good use of it that you can talk about?
Good question. No, I can't give you an example, but I can tell you that they are out there and leveraging the underlying hardware. I think that the challenges that we're facing right now and we're making good progress on, we told you about Andromeda. The key question here is how do we provide isolation while opening up the raw capacity of our hardware? And that's getting to come along further and further. I would encourage basically anybody in this room to try it out. In other words, in terms, if you need bandwidth, and certainly if you need bandwidth at scale, Google Compute Platform is running on the exact same infrastructure that powers Google Search, that powers all of Google services.
Exactly.
Yeah.
Okay, I guess, go ahead.
Two questions. One, a quickie. Do you see any room for SDN in the LAN? And just, does it have a role? But the second one is more interesting, this I/O gap. If I think about that, it's a little like batteries, which seem to be the one thing that don't move with Moore's law. Can you spin me forth the scenario where the I/O gap problem doesn't get solved, and what does that mean for your architectures?
Okay, good questions. First question, yes, there's a huge role for SDN in the WAN. We actually, about 3 years ago or so, described our SDN architecture for B4, our private WAN, in some detail.
Sorry, I meant LAN.
LAN. So, sorry, I don't know what LAN. This is a data center network. It's sort of a LAN. Home network would be a LAN, something in between those. I/O gap. I/O gap has to get solved, I would say. In other words, there is too much at stake for it to not get solved because essentially the alternative is that we stop innovating. So I think it's going to be really an exciting opportunity there. And what we're seeing now is disk is going to be around for a long, long time. It is the cheapest way to store bits. If you look at probably, I'm going to guess, your use of disk storage, you create lots and lots of videos, photos, etc. You access them rarely. You still want them around forever. Now there's going to be this new tier, probably stored in flash, probably stored in non-volatile memory that has much, much lower latency, much higher bandwidth characteristics than disk does. Just a tremendous opportunity to open that up at data center scale and change the programming models. I mean, it's a much longer answer, but I'm personally very, very excited about how programming models can change around this next generation of storage. And will it? Yes. How fast will it is, I think, the question.
Okay, I think if you ask a short question and you give a short answer, we can have one more, last one. Okay, go for it.
Okay, so my question is that you talked about using merchant silicon to address your networking issues. Would you be able to share a little bit about any ASIC approaches that you're using?
So we are buying merchant silicon ASICs from vendors. So in terms of ASIC solutions, none. In other words, just as we might leverage merchant silicon for compute, we've been doing the same thing on the networking side. We've been writing, if you will, Moore's law on the network side to have more network capacity, keeping up with the rather insatiable bandwidth needs of the servers that are growing in their bandwidth requirements.
Thank you.
Okay, I think with that, thanks again, Amin.